Today's speaker is Emily Nardoni, and the title is Duality of Adjoint SQCD from Argyres Douglas theories. Please start.
Okay, thank you very much. And thank you very much for the invitation. I'm really happy to be here and visit Kyoto, not too far away from where I'm based in Tokyo right now. So yeah, I'm going to tell you about some work that I did last year with my really fantastic collaborators, Kazunobu Moriyoshi and Jaewon Song. And the title has this like Argyres Douglas theories in it, and I'll explain what I mean by that class of theories throughout the talk. So I want to begin with just some like very general motivations as to like why I'm interested in this subject. And really, it goes back to that string theory is, of course, a very powerful framework for generating and studying interesting quantum field theories. This is really where I like to use string theory to better understand quantum field theory. And in particular, these sorts of, you might call them geometric engineering setups, where I realize quantum field theories as the low energy limits of configurations of branes in string theory is a really useful way to generate generically strongly coupled and interesting quantum field theories. So I like to view this like as some sort of machine or black box, where as input I have the details of my brane configuration, like that's some compact manifold that I'm like compactifying the branes on maybe, and like details of some sort of topological twist in order to preserve, usually we want to preserve some amount of supersymmetry in the low energy quantum field theory so that we have some, computational handle on its properties. And then the output is some quantum field theory. Often we're interested in, again, supersymmetric quantum field theories, especially for computational reasons. And this quantum field theory is really generically strongly coupled in this landscape of the sorts of things I can get from these brane constructions. And so that in itself is interesting. And these quantum field theories are also characterized, of course, by some of this initial data, and also by, in particular, the topology of the internal space involved in the compactification. And so really the big upshot to this program is it allows us to generate and not just generate, but organize geometrically large classes of strongly coupled quantum field theories. Because, of course, now we can trace their properties back to different properties of the geometry and try to get some additional handle on computing their strong coupling properties. So really my motivation is to use this sort of geometric engineering setup as a rich testing ground for exploring general aspects of quantum field theory. So I like to think of this kind of abstract blob as like a general space of like theory space of different quantum field theories. And we begin in our graduate programs learning about weakly coupled Lagrangian gauge theory, which is like some lives in some corner of this theory space. And that's a very well understood corner of this space. We have like really nice perturbative tools for understanding Lagrangian gauge theory. But of course, there are many other corners of this space, and some of these corners have really been elucidated by these sorts of string theory constructions. And in particular, we know in the last several decades of work in this subject, working on string theory and quantum field theory, that there are quantum field theories that are actually really inherently quote unquote non-Lagrangian in the sense that there's no useful Lagrangian that describes their like conformal point or describes like this quantum field theory. So these are quantum field theories without any tunable parameter at all. And so these would have been thought of as extremely strange, but now we know they're completely generic by looking at this landscape of quantum field theories I can get from string theory. And so this allows me to probe new corners of this sort of parameter space in quantum field theory. And really, like the takeaway from these sorts of ideas is that there are often really surprising and useful interconnections in this space of quantum field theory, so between different quantum field theories. So on this sort of diagram, I'm imagining that these arrows that connect different corners of this space, they might be some renormalization group flow, they might be some sort of duality, like an IR type duality between quantum field theories or limits of string theory. They might be some decoupling limit in string theory, which I can think of really as a cross-dimensional renormalization group flow or cross-dimensional duality, depending on the situation. It might be like ADS CFT holography relating like theories of gravity to conformal field theories or so on. But all of these arrows let me carve out more and more bits of this space and learn more about general or generic properties of quantum field theories on the one hand, and also specific properties of interesting quantum field theories we might care about by utilizing some of these specific arrows on the other hand. So the general goal is we want to harness these sorts of interconnections in order to develop new and more powerful tools for computing observables of these quantum field theories. And by observables, I mean, for example, Tooft anomalies. I mean, data about the generalized symmetries of the quantum field theories. I mean, like, for example, the quantum numbers of operators. So like, for example, maybe BTS operators in the theory or different classes of operators. I mean, maybe different partition functions or indices, details about the moduli space, for example, dimensions of the moduli space, central charges, and so on. That's what I mean by QFT observables in this context. And so, of course, duality is a very powerful tool for studying quantum field theory and for relating different quantum field theories to each other. And so straight from the get-go, I want to explain what I mean by duality in this, for the purposes of this talk, is I mean an IR type of duality. So this means that I have two quantum field theories that might look very different at high energies, totally different gauge groups, matter content, etc. But they are argued or known to flow at low energies to precisely the same conformal field theory, or I'm going to be interested in superconformal field theories. And so in that sense, they are IR dual to each other. Their long distance physics is exactly the same. And so I can learn about the long distance physics of one from the other description or vice versa, whichever is more useful. And so these are quantum field theories, like we also say that they are in the same universality class. So this is a powerful tool, and this is what I mean by duality throughout the rest of this talk. So with that being said, the plan for the rest of this talk is I'm going to explain to you a proposed duality of this type that my collaborators and I discussed in our paper that relates, on the one hand, a Lagrangian gauge theory, which is basically an n=1 supersymmetric version of QCD plus some extra matter content. I'll tell you next more details about this left-hand side of this duality. And on the other hand, one of these inherently strongly coupled, quote unquote, non-Lagrangian theories, which is it's related to by our G-flow, one of these so-called Argyres-Douglas theories, which are n=2, 40 n=2 theories. And we're going to do some deformation that flows to an n=1 fixed point, and we're going to argue that this fixed point that this class of theories flows to is the same fixed point that this class of Lagrangian gauge theories that are cousins of QCD flow to. And so then I'll tell you more details about this side of the duality, but that's the punchline. And so for the rest of the talk, first I'm going to tell you a bit of a story about this adjoint SQCD and its fixed points. And then I'm going to tell you a little bit of a story about these n=2 Argyres-Douglas theories and their n=1 deformations that we're going to be interested in here that form this duality. And then I'm going to tell you some of the non-trivial checks that should give you some confidence that this is a good conjectured duality. Very difficult to prove dualities in general, so you should do as many checks as you can possibly get your hands on, is the state of things. So are there questions before I get into like the meat of the talk? Okay. So first, let's talk about adjoint SQCD, which is my favorite theory. So first, I would like to perhaps remind you of the most well-studied canonical example of an IR duality of this type in supersymmetric gauge theory, and that's the Seiberg duality of 40n equals to 1 SQCD. So this is a very nice, well-known story that was first noticed by Seiberg in the 90s, where on the one hand, we have 40n equals to 1 SQCD, by which I mean the SUN gauge theory with some number, call it NF, of fundamental and anti-fundamental chiral superfields. So like the ones whose like scalars are like the squarks, and fermions are like the quarks. So like these chiral superfields. So on the one hand, I have this n equals to 1 supersymmetrized version of QCD with some number of flavors of fundamental quarks. And on the other hand, on our B side of the duality, we have a different gauge theory. So we have an n equals to 1 theory with SUNF minus n being the number of colors or like related to the rank of the electric gauge group theory with some same NF number of fundamental and anti-fundamental chiral superfields, but now fundamentals of this different gauge group. Plus there are some, I'm not writing all of the details, but plus there are some additional singlet like superfields, chiral superfields that are singlets of this gauge group. Plus there's some superpotential that couples all of them together. And then it is known that these two theories flow to the same fixed point at low energies, so they are dual in this sense, and it's a 40n equals to 1 superconformal field theory. So some comments. So first of all, this statement of Seiberg duality, it's not valid for every value of these parameters. So it's valid in particular in a conformal window of parameters of NF. I could write it NF as a function of the number of colors, for example. So NF less than 3n and bigger than 3/2 n. This is the asymptotic freedom bound on the right-hand side for this theory. Another comment is that part of the reason this is so useful is it exchanges strong and weak coupling. So the couplings are related by like an inverse. So when one of the theories is strongly coupled, the other is weakly coupled. And so I can use the weakly coupled description to like learn about the strongly coupled dual. And of course, there are many checks of this duality. So everything from the global symmetries match on either side, the 't Hooft anomalies match, of course, all the gauge invariant chiral operators can be shown to match on either side, moduli space. You can look at deformations of each theory and check that doing one deformation and its analog on the other side give the same consistent results. The superconformal index matches, which is an extremely strong check. The fact that in this case, the superconformal index is identical on either side of the duality, that's a very, very strong check, and so on. So the theories that we're interested in today are sort of cousins of n equals to 1 SQCD, where I add chiral superfields in the adjoint representation of the SUN gauge group. And so in general, I can add at most 2 such adjoint chiral superfields and still be compatible with asymptotic freedom, which we want because we want to do something interesting. We want to study like an asymptotically free theory. And the statement is that when I add up to these 2, 1 or 2 of these chiral superfields, The IR phase of the theory, of course, much like in the case of normal Seiberg duality, will depend, or normal n equals to 1 SQCD will depend on the parameters like number of colors and enough. And so the statement is that the possible interacting n equals to 1 superconformal fixed points that I can get within this class of theories, like n equals 1 SQCD plus up to these two adjoints, they're classified by their superpotentials. And so this is work that was done by Ken Trilligator and Brian Wecht back in the early 2000s. And so the statement is that I can add superpotentials for these two adjoint chiral fields, and basically they checked that by all sorts, like any superpotential deformation I can add, they checked which are the ones that lead to non-trivial fixed points, that you can do some analysis and argue that it will be some relevant deformation that will drive a flow to a new fixed point. And by doing this analysis, they came up with this list of the possible superpotentials which lead to fixed points in this space of theories, adjoint SQCD. And kind of interestingly, this list follows an ADE classification. So ADE classifications come up all over the place in physics. Here, actually, so here the reason, or you can see it's an ADE classification because these superpotentials are, which I've labeled by their like ADE label, are precisely the form of Arnold's simple surface singularities, these like ADE simple surface singularities, and which of course are in correspondence with the simply placed Lincoln diagrams. That's where the ADE comes from. But kind of interestingly, like just as a side note, actually in this case, it's still not well understood like why these fixed points are classified by ADE, like why this came out. Like they did this analysis just like in terms of what's relevant in this class of gauge theories and what drives me to a fixed point. But the deeper reason as to like why we get this ADE classification is still not well understood and is still, I think, an interesting question. But okay, so we get this class of fixed points of adjoint SQCD. And so now the statement is that there are proposed Seiberg-like dualities, so analogs, generalizations of Seiberg duality for various of these theories. So in all cases, the proposed dual is going to be some, gauge theory with some different gauge group. I'll say more on that in a moment. And so the first generalization was by Kutuzov and Schwimmer for these AK theories. And so these AK theories are just one adjoint theories. So you can see like here, I just have a mass term for the second superfield. And so it's equivalent to just, at low energies, I just integrate it out and I'm just left with the theory of one superfield. So with just one adjoint chiral superfield, the fixed points of this theory are labeled by this trace x to the some power k plus 1 superpotential. And this looks like it's like super irrelevant. K can be arbitrarily large, but it's actually dangerously irrelevant in that you can always find a range of parameters, even for very large k, where this will drive you to a new fixed point and become relevant. Like the gauge interactions will force this thing to become relevant. And the rest of these are all like really non-trivially two adjoints. Maybe I should say k equals 1 is also obviously like x squared plus y squared, that you just get right back to normal SQCD and you recover everything you know about normal SQCD and Seiberg duality in that case. So these sort of Seiberg-like duals have been proposed by Kutuzov and Schwimmer for AK, Brody for the DK cases, and Kutuzov and Lin for the E7 case. It's kind of an interesting story. Not every one of these superpotentials has a proposed dual. And this is related to the fact that all of the duals that have been proposed, they require some truncation of the number of independent chiral operators in the theory. This is called the chiral ring. And like the total number of these independent operators is like the number that goes in the dual gauge group, which is kind of interesting. So for example, in this AK case, you can see like I have this trace x to the k plus 1 superpotential. So the F terms, just like the equations of motion that follow from the superpotential, tell me that like trace x to the power, which is bigger than k, is just 0 by the F terms. So I don't get independent chiral operators that involve more than this number of power, like this number of products of my adjoint chiral superfield. And so I'm truncating to, in this case, like k elements of these adjoint valued, like, or adjoint products of adjoint composed chiral operators. And this alpha is like k in this case, just for example. And in these cases, there actually is no apparent truncation of the chiral ring. And there are actually still some open questions regarding proposed quantum truncations of the ring that aren't seen at the classical level for the D even cases and the E7 case. This is something that was actually my first research project in the field as a graduate student. So I think it's fun personally to come back to this subject, which is still not that well understood. There are still puzzles with this very basic class of Lagrangian gauge theories and their proposed Seiberg-like duals. So if that's something that piques your interest, there are still open questions, even in just this kind of simple class of theories. But okay, so today, the theories that are going to be dual to our proposed dual to our Argyres-Douglas theories are just the AK case. So just the case with one adjoint, like I can think of again, like just integrating out the second guy. And so these are the fixed points that come from these superpotentials where I add a power of one adjoint. And these have magnetic, again, like Seiberg-like duals. And the statement today is that we're proposing an additional dual for this case, in addition to the Kutasov-Schwimmer Seiberg-like dual. Okay, so that's my little story about adjoint SQCD. And these are the theories that are going to play a role in the rest of this talk. So now let me say something about these 40 n equals to 2 Argyres-Douglas theories and their n equals to 1 deformations. So yeah, these Argyres-Douglas theories are, again, some of these like non-Lagrangian theories that are maybe some fun, interesting corner of this theory space of quantum field theory that we would like to understand.
So just to remind myself,
Yeah.
All this ADE classification on the previous slides, so the magnetic dual, are they Lagrangian or non-Lagrangian theory in general?
Good. So Lagrangian, I mean, they're strongly coupled, right? So like, you know, the idea is that you're flowing to some interacting conformal fixed point at low energies, but I have a UV Lagrangian description, which is precisely like, the Lagrangian of SQCD plus like the appropriate this appropriate superpotential.
So for those classes, has the super conformal indices being applied to check the cyber dual?
Yes.
Or they have?
Yes, so absolutely. So for all of these cases, those checks have been done, but it's a little subtle. So so for Seiberg duality, the indices match, like there's an identity, like some integral identity that shows that they are identical.
Mm-hmm.
For the I don't remember if I think for even AK, like they've checked that in some limits they match, but there's no proof that they're identical, like for all values of the parameters. So, but they've certainly been checked in some limits that they match. And then for these cases, it's actually even more subtle because like the identities aren't known that would prove that they match. So instead you look at them in certain expansions and to some order.
Down to our ignorance about the property of elliptic gamma function.
That's right.
I see. But
yeah, that's right.
But because of others cases that we're all happy with this, so then we assume. I see.
That's right. However, like I said, there are still some puzzles with these guys. And so it's still interesting to ask if we can expand, even if we could expand the, okay, so for example, for this like E7 theory, the dual is like this alpha is 30. So this is like an SU30 NF minus like number of colors. So I end up with some like very high rank gauge group. And it's like, even if I want to just expand the superconformal index to some power in the fugacities, it's very difficult to do so to any like sort of high power because of this like super high rank gauge group. So not only do we not know like the proposed identity of the elliptic gamma functions and stuff, but like furthermore, we can't even expand the index just computationally to the right power to really convince ourselves convincingly. So there's definitely still work to be done there.
I see, but bottom line is all these are Lagrangian. So, but you have.
That's right. So I can just write it down from the Lagrangian. Okay. So I have a Lagrangian, so I can write down the index, but then it's still hard to show if they actually, like if these,
I appreciate even the original case was hard. Well,
yes, of course.
Thanks to the identities.
That's right. That's right. Okay, so these 40n equals to 2 Argyres-Douglas theories, these are theories that were, like the very first instance of these guys, they were found at singular points on the moduli space of different 40n equals to 2 gauge theories. So like special singular points where BPS states, which were with mutually non-local like electric magnetic charges, become light at the same time. So like we can't write a Lagrangian description of like a monopole and like a dion like becoming light at once. Like we don't know how to do that. So in that sense, it's kind of natural to think that we don't have like a good Lagrangian description of these guys. Instead, we've understood them from one perspective as like limits on the moduli space of various gauge theories. And the first instance of such a interesting singular point was studied by Argyres and Douglas, and so that's where the Argyres-Douglas name comes from. So we've kind of just tacked on the name Argyres-Douglas to any type of theory like this that comes from like basically like mutually non-local BPS states becoming light at the same time. They were looking at SU3 pure like super Yang mills, and then arguing that at this singular point, you get this like, interacting, interesting conformal field theory, even if I can't write like a proper Lagrangian description of it. But like then there were student generalizations to like points on other gauge groups. And now more generally, like this means like any theory with these sorts of properties that I'm describing here. So I'm using the word non-Lagrangian, and by this I really mean intrinsically strongly coupled. Like we don't have an n equals 2 preserving Lagrangian that describes the conformal point of these theories. Although I do want to emphasize that there are some cases in which we have dual n equals to 1 Lagrangian quivers, like quiver gauge theories that are argued to like flow in to the same like Argyres-Douglas points. So there's supersymmetry enhancing from n equals 1 to n equals 2. So there are some cases where we do have some useful dual like UV Lagrangian description, but we don't have a description of like the conformal point itself, and we don't have an like n equals to 2 Lagrangians that describe these points. So yeah, this was an interesting story that especially like in these years, there's a lot of work done on these. And one of their defining properties is that they possess relevant operators in their spectrum that have fractional scaling dimension. So some of their Coulomb branch operators, like the chiral operators that parameterize the Coulomb branch of the moduli space and are relevant, have fractional scaling dimension. And this is like the fact that this is fractional is like one manifestation of the fact that these are quote unquote non-Lagrangian or intrinsically strongly coupled conformal field theories. So now we know various constructions of these Argyres-Douglas type theories from string theory. And I'm going to briefly tell you about one class of these so-called Argyres-Douglas type theories and how you construct them from a class S construction, meaning from like M5 branes or starting from the 62,0 superconformal field theories. There are other string theory descriptions of these, like from type 2B, for example, but for the purposes of my talk, I'll tell you a little bit about this construction. So I'm going to focus on the class, which the naming conventions are really awful, and I apologize, but the class, they're called DPG, or where the G stands for the fact that in this construction, we're starting with a 2, 0, the 62, 0 superconformal field theories of type G. And in this talk, I'm going to focus only on the A type, or like SUN type of 2, 0 theories. And compactified on a sphere. And the sphere has particular properties. It has 2 punctures. And one of these punctures is just a regular puncture, which is a full puncture, which means that if I started with the type G 2, 0 theory, basically you can think of it as imparting like a G flavor symmetry in my low energy quantum field theory I'm getting at the end of the day. And the other puncture is a so-called irregular puncture. And so the irregular puncture is labeled by a positive integer p. This is the p of the DPG. And so the p is basically, it's the fractional part of the pole that the Higgs field in the associated Hitchin system that describes like the puncture has like near the puncture. So if you don't know what those words mean, that's okay. They're not important. Like the thing that's important is that I have an irregular puncture, which means it's described by a pole with a fractional part. And the fractional part, it depends on n, but it also depends on this integer p. And just a full puncture, whose role in life is to impart, like in this case, SUN flavor symmetry to my low energy quantum field theory. And so at the end of the day, when I compactify 6 dimensions down to 4 dimensions, for this class of theories, I get a 4-dimensional n=2 preserving conformal field theory, which is one of these Argyres-Douglas type theories. Called this like DP AN-1 or SUN for the cases that we're talking about. If you follow the literature, you might like also see this sort of labeling, and this sort of labeling, I've color coded it. So you might label it by the irregular puncture, so by like this integer p basically, and by the regular puncture, which is in this case like a maximal or full puncture. And so some people like label it by those 2 punctures on the sphere. So it's Argyres-Douglas in the sense that, just like, for example, like if I take G = SU2, so I'm taking like the 2, 0 theory of type like SU2 on this 2-punctured sphere, then this construction coincides with the maximal singular point on the Coulomb branch of just pure like SO2P super Yang-Mills. So it matches onto one of these like types of limits that I was describing on the other side, but this is like some larger generalization of a theory of that type. And so I want to emphasize that kind of all of the funny features of these Argyres-Douglas theories, like this like non-Lagrangianness and this like fractional dimension Coulomb branch operators, these are really coming from the irregular puncture. That's like something I want to emphasize. And the other thing to emphasize is that these sorts of geometries that lead to n=2 superconformal field theories are really rigid in the sense that like I can only have one irregular puncture on this sphere. Like in the general class S program, where I compactify a 2, 0 theory on a Riemann surface to get some like n=2 or n=1 theory in 4 dimensions, I can generally consider like Riemann surfaces with like arbitrary, genus and arbitrary number of like regular type punctures, and I can get something interesting out. But the statement is, once I have irregular punctures in the game, the type with this like fractional pole, I'm limited to just genus 0, like the sphere, and like only up to 1 like irregular puncture. So These are like kind of special in the more general class of theories I can get by compactifying 2,0 theories on a Riemann surface. And I don't want to spend time on this, but just as a comment, in recent years, my collaborators and I discovered, or like were able to write down the large N holographic duals of like this particular class of theories we're talking about in 11D supergravity. And that's pretty interesting because now we have like new like holographic duals of these guys. You can like understand how the features I was just describing on the previous slide, like for example, like I'm compactifying on this like punctured sphere, and you can understand in the holographic dual, like in this like, you know, supergravity dual, how that sphere is like dual to like a disk with an orbifold singularity. And some of the funny features of the Argyres-Douglas theories come in this language from the fact that I'm actually doing a non-standard type of topological twist on this disk with an orbifold singularity. And so I'm not going to say more about holography in this talk, but in future directions, like I think it's useful to keep in mind that these N=2 Argyres-Douglas theories now have known holographic duals, and there's hopefully something you can do there by utilizing that picture. And especially since I want to relate these to like, you know, SQCD type theories, it would be interesting to understand that relationship better from this holographic perspective. But I just wanted to highlight that since I was also involved in those series of works some recently-ish. Okay, so, but we're focusing on this class of Argyres-Douglas theories. So again, 4D N=2 theories of type DP SUN. And I just want to highlight some of the main features that we're going to be matching here, or that will play a particular role. These were all computed by other people whose references are on the previous slides, or please ask me if you're wondering. And one caveat is for the rest of this talk, I'm going to restrict entirely to this case where these integers p and n are coprime. This is mostly for technical reasons. You get like additional symmetries and stuff in our duals if like this isn't the case, but just like a disclaimer. So now I'm going to, like all of these formulas will be much, much more complicated if I'm not looking at the case where p and n are coprime. So I'm only going to be writing down formulas for this set of integers from here on out. But okay, so these are N=2 like conformal field theories, and so they have an SU2 times U1R symmetry. That's one thing they have, obviously, as N=2 theories. Their central charges can be computed, so you know we can write their A and C central charges. They depend on these integers p and n, both positive integers. I emphasized that they have this SUN flavor symmetry, which was coming from this full puncture in this class S description. And so, for example, I can compute the flavor central charge of that SUN flavor symmetry, global symmetry, and it again depends on p and n. The actual numbers don't really matter, but just to show, you know, we can compute these things. Furthermore, so the moment map operator associated to this SUN flavor symmetry, by which I mean like the primary operator in the conserved current multiplet for the SUN flavor symmetry. It's like charged under the SU2R symmetry, and it's parameterizing like the Higgs branch associated to this SUN flavor symmetry in the theory. This is known by studying the Schur index to satisfy this particular relation, so that traces of powers of this moment map operator are trivial, so that it's truncated at a maximum power. This will play a role in matching in a duality check that we'll do later. So this is the statement that these Argyres-Douglas theories, their Higgs branch is a nilpotent orbit. Anyways, that's reflected in this sort of Higgs branch relation for the moment map operator. Furthermore, we know that they have Coulomb branch operators that parameterize the Coulomb branch of their moduli space. And we also know the scaling dimensions of these Coulomb branch operators. So these are operators that are charged under the U1R symmetry. The moment map operators are charged under the SU2R symmetry. And we know their dimensions. Again, they depend on like N and P, and there's some spectrum of them. Okay, so that was my lightning introduction to this class of Argyres-Douglas theories. And the key useful idea that I want to use is that, or that's especially useful just in general in this sort of geometric engineering program, is to view like these sorts of interacting, perhaps strongly coupled superconformal field theories that arise from these geometric constructions as building blocks, from which that I can really think of as like generalized matter sectors and use to build even more general, interesting quantum field theories. So this is kind of like the ethos behind a lot of this like geometric engineering sort of work. And it's kind of just a generalization of the idea that in a free theory, I have like, free matter, and I can think about building more general, weakly coupled gauge theories by coupling matter together, for example, by like gauging subgroups of global symmetries that the matter transforms under. And so this is saying that we can transfer that idea not just to like weakly coupled building blocks like free vector multiplets or something, but even these sort of like strongly coupled building blocks like these like n equals to 2 Argyres-Douglas theories. So I'm going to think of this Argyres-Douglas theory as some thing. It's some strongly coupled thing that I'm representing by this circle. And it has this flavor symmetry, this SU1 flavor symmetry. And we can think about coupling it to like other building blocks by, again, like gauging like subgroups of this SUN flavor symmetry, for example. So that's a useful idea in general. And so now we're going to use that to look at a deformation of these are n equals to 2 theories. So the first step is to take this n equals to 2 building block, this Argyres-Douglas theory that I'm just representing in this sort of quiver-like notation that I just described, and we're going to add a superpotential deformation. And so in particular, this is a superpotential deformation. I'm just going to add to the superpotential the Coulomb branch operator in the Argyres-Douglas theory of smallest scaling dimension. That's what I mean by this U0, like the operator, the Coulomb branch operator of smallest scaling dimension, and it has dimension p+1 over p. And by adding this deformation, you can argue that this is a relevant deformation and the theory flows to a new fixed point. And it also breaks n equals 2 supersymmetry to n equals to 1 supersymmetry. Okay. So I can see what happens when I add this deformation. The first thing to check is, okay, like what is the superconformal R symmetry at the putative new fixed point? And so this you can check. Basically, like what you do is you view like our n equals to 2 R symmetry of the Argyres-Douglas theory from the n equals to 1 point of view. It involves 2 U1 flavor symmetries, or one of them generates the n equals to 1 R symmetry, and one of them generates like a flavor symmetry from the n equals to 1 point of view. And then I can compute the like the R symmetry of the putative superconformal fixed point after adding this deformation it's going to be in general some mixture of these two U1 symmetries, and I can compute it by A maximization, which is very, very useful for looking at renormalization group flows amongst n equals to 1 theories. And so I can do this. I'm not really describing all the details, but you can. The point is, this is an explicit computation. You can check, and you can see that this leads to a particular form of the superconformal R symmetry at the n equals to 1 fixed point, and it allows me, because the A and C central charges are related to like anomalies involving the superconformal R symmetry at the fixed point, it allows me to compute the central charges, and so I can compute the central charges. And the first observation is that these central charges of this theory plus this deformation exactly match the central charges of a chiral multiplet in the adjoint representation of SUN with this particular R charge 2 over P plus 1. So that's the first step. We can argue that we flow to this fixed point, and this fixed point has the same central charges as a particular adjoint chiral multiplet.
Is that epsilon is the parameter how mixing?
Yes, exactly. Exactly, yeah. And it depends on this, it depends on P and N, like how it mixes, you can compute it, and then you can use it to compute the central charges. Yeah, that's right. Furthermore, I can compute the Schur index of this deformed theory. And I can check again that the Schur index, it's too difficult, or we don't currently know how to compute like the full superconformal index, unfortunately, for this configuration, but we can compute the Schur index is like one limit of the full superconformal index, which you can compute for these Argyres-Douglas theories. And so I can compute this limit of the superconformal index and check it also matches the Schur index of an adjoint chiral multiplet with this particular R charge. Now for P equals 2, so this like D2 SUN type theory with this superpotential, it's actually known that this theory flows to free fields in the IR. It just flows to a free chiral multiplet in the adjoint of SUN, which matches, like if I put P equals 2 here, R equals 2/3 is the R charge of a free chiral multiplet in a 48 equals to 1 theory. So for P equals 2, I'm just flowing to some free chiral multiplet, and all of this makes, matches what I just saw. But the, observation is that for more general P, I'm flowing to some, interacting thing. It's like some interacting fixed point, but like it's an interacting fixed point that looks like a G adjoint chiral multiplet or an SUN adjoint chiral multiplet. So kind of the tagline is that this this deformed DPG type theory with this N equals 1 deformation of this type is kind of behaving like a G adjoint chiral multiplet. It's not a free field, but its data matches that of like this this chiral multiplet. Okay, so that's encouraging. We want to match on, or I'm telling you that we want to match on to a theory with adjoints. And so we're on the right track. And so the next step is we take this N equals 1 deformed theory and we couple to, we basically are just coupling to SUN SQCD with NF fundamentals by like gauging the diagonal subgroup of the SUN flavor symmetry with an SUN flavor symmetry of like a theory with NF fundamentals. And so that's it. Then I get this, interacting conformal field theory that I'm representing by this diagram. It preserves N equals to 1 supersymmetry. And this is precisely like the theory that I claim is dual to our adjoint SQCD theory, where the P of the DP SUN or Argyres-Douglas theory is like the thing I was calling K in the first part of the talk, like the power of the adjoint chiral superfield in the superpotential. And so the claim is that these flow to exactly the same fixed point at low energies. And so this is yet another dual description in addition to our magnetic Seiberg-Leck dual of this class of gauge theories. Okay, so it's kind of a crazy claim, but maybe I've already given some evidence by explaining how these theories kind of already behave like adjoint chiral multiplets. But let's do some more checks and try to convince ourselves. So the first comment is that much like for normal Seiberg-Leck dualities that are only valid within some conformal window of the parameters, this claim is only going to be valid within some, associated conformal window of the parameters. And so we can compute what that window is, and we can compute that. First of all, there's the asymptotic freedom bound on the right-hand side, that bounds like how big NF can be so that this proposed duality makes sense. And so that gives this right-hand side. And on the left-hand side, I can compute, like, basically what I need to check is that when this like n=1 deformation is a relevant deformation from our like theory with no superpotential in this like Argyres-Douglas, deformed Argyres-Douglas dual description. That's kind of like another A maximization analysis, basically. And so I can check that and compute. Actually, I get a very complicated answer over here, but this very complicated answer, which is in our paper, is basically like n over p. It's like very, very, very close to n over p. Like if I look over all ranges of all parameters, it's like really, really close to n over p. That's what this squiggle means. And so this is the proposed like conformal window of this duality. And I can compare that with the window for which this fixed point exists in adjoint SQCD. So clearly I can only claim this in a window where the fixed point exists to begin with. There, like the right-hand side of that existence bound comes in that description from asymptotic freedom. And the left-hand side comes from basically like there's a vacuum stability condition coming from like needing like a stable supersymmetric vacuum to exist in the theory. You can check that that gives some bound on like the number of flavors. And so we get very similar windows. It's not necessary that we get exactly the same window, but it is of course necessary that these windows overlap if we're claiming a duality of this fixed point. But not only do the windows overlap, but they actually exactly match at large p, which is, I think, pretty interesting. So like the large p theories, like the claim is like as p gets large, these theories are dual for the entire range that the fixed point exists on like the Lagrangian side of the duality. That's the claim.
So for P=1, it's same with n=1 SQCD.
Good. Yes.
And then that lower bound is 3 half.
Good. So I'm okay. So I should say like in all of these, like I'm assuming that P is 2 or more. So like everything I'm saying like doesn't make sense for P less than 2. Yeah. So I don't know of an Argyres-Douglas dual of pure SQCD, but this is valid for P2 or greater. Yeah. And you can do more duality. I'll kind of maybe just I'm running a little bit out of time. Maybe I'll just run down the list so I can check that the global symmetries that I can identify on either side of the duality match. Of course, that has to happen. I can also, obviously, I want to check the central charges. And so this is, some non-trivial computation and this like n=1 deformed Argyres-Douglas theory. It's the same sort of like A maximization computation I'm doing on the other side, but it's a different setup. So it's really like a different computation. We compute the central charges. They're, not, that simple. They depend on N, P, and NF. And we can check that the central charges we compute on this Argyres-Douglas side of the duality exactly match those of adjoint SQCD from the Lagrangian description. Furthermore, like I said, we don't have access to the full superconformal index of the Argyres-Douglas theories, but we do have access to their Schur limit, and we can check again that the Schur limit matches on either side of this duality. We have a further match for p=2, which is the lowest value of p we can consider. So p=2, n=3, and there the full index matches identically. So this I would say is actually a very strong like piece of evidence. So for p=2, n=3, this is just I mean very likely true. Like the full superconformal indices just match identically. We don't have access to this strong check for other values of p and n, but okay, we can check that the Schur limit at least matches for these other cases. We can also, of course, check the mapping of chiral operators on either side of the duality. The thing I want to point out is that, so these chiral ring operators, these traces of products of the adjoint chiral superfields in like the Lagrangian adjoint SQCD side of the duality, they map in the Argyres-Douglas side to the Q squared descendants of the Coulomb branch operators of the Argyres-Douglas theory. So remember, we started with an n equals to 2 theory that had Coulomb branch operators, which are primaries of n equals to 2 Coulomb branch multiplets. And we broke to an n equals to 1 theory. So these multiplets break into 2 n equals to 1 like submultiplets. And the second order descendant of the Coulomb branch primary operators are again scalar operators, which are primaries of these other n equals to 1 multiplets. And it's precisely these guys that map onto my chiral ring operators in the Lagrangian side of the duality. I can match the mesons of the adjoint SQCD theory, like Q twiddle with like some power of the adjoint in the middle, to products of our moment map operators with like the Q and Q twiddle I have on the Argyres-Douglas side. Of course, I have the quarks, like the fundamental fields on either side, so the baryons kind of match trivially, and so on. And the fact that I get this correct truncation of the mesons, like that is we see in like the SQCD side, to like this is truncated to j equals like p minus 1, is precisely reproduced on the Argyres-Douglas side because of this like Higgs branch relation of the moment map operators that I pointed out earlier. So we actually get like the correct number of mesonic type operators on either side of the duality in a pretty non-trivial way. Like this is like a quantum effect in the Argyres-Douglas theory. Now, one comment is that the Coulomb branch descendants, these should also truncate. Like we know in adjoint SQCD, these do truncate to like some maximal power P here. And that we don't see immediately on the Argyres-Douglas side. So this is what this is saying is if you believe this duality, this is a non-trivial prediction for a truncation of the chiral operators of this like n equals to 1 like deformed theory. So we can't verify explicitly. Maybe one comment is that this isn't so uncommon in these dualities, like even in like the Seiberg-like dualities, it's common for a truncation which is classical on one side of the duality to be quantum on the other side, and like difficult to like something that you might not actually know from any other means except for the like the dual like classical relation. And so this is a prediction, and it would be nice if we can confirm this by some other means. Like if we could expand the superconformal index to the right, at least expand it to the right order to like verify this or something. So that would be an interesting thing to make sure we can check in the future. But again, like these exactly match, like everything I just said exactly matches for this case of p equals 2, n equals 3. So at least the minimal such case truly is a duality. I think there's no ambiguity whatsoever. Everything is like totally explicit on either side. Okay, so I'm almost exactly out of time. So I'll just summarize that I motivated this new non-Lagrangian dual of a class of 40 n equals to 1 fixed points in adjoint SQCD. And I'd like to end with just some like laundry list I have of open problems and speculations. So at present, this proposed duality is most interesting for learning about this like non-Lagrangian dual, right? So like, for example, I said that this gives me some prediction about the chiral operators in this like non-Lagrangian, like deformed Argyres-Douglas theory. On the other hand, it would be, so the first comment is it would be very interesting to push this program further to like, can we use this proposed duality to like say something more about the superconformal index for these Argyres-Douglas theories, which we don't know how to compute at present. For example, can we like use this to do something more non-trivial with the Argyres-Douglas theories? But on the other hand, I said that there are already puzzles just on the Lagrangian SQCD side of the duality. And so it would be extremely interesting if we could extend these results to the 2 adjoint case, not just the 1 adjoint case. And we have some ideas on how to do that, although we haven't like been able to flesh it out yet. And if we could, then perhaps we could, use this in the other direction and shed a light on these lingering puzzles with the two adjoint theories. So that would be very interesting. And I hope that we can do something with that in the future. Of course, one can hope to extend this to other types of DPG theories and their deformations. Furthermore, I said at the beginning of the talk that these DPG theories have holographic duals that were understood in recent years. And so it would be very interesting if we can understand the duals of these deformations. And we don't know a holographic dual for these adjoint SQCD fixed points. And so it'd be very interesting if we could use this program to learn something about the holographic duals of these fixed points of adjoint SQCD. And furthermore, it would be really interesting if we could use this program to get a hint as to, in this general geometric engineering business, how to glue these sorts of Argyres-Douglas building blocks via the irregular punctures. So, I was saying that, gluing and building more general, strongly coupled quantum field theories from these strongly coupled building blocks is just, it's interesting and productive in general. But the way we know how to do that is in terms of flavor symmetries associated to regular punctures in this class S language. And so it would be very interesting if we could learn new ways to combine these building blocks that involve these irregular punctures. And now that we have these dual descriptions of the Argyres-Douglas theories, and we have these holographic duals of the Argyres-Douglas theories, I think it's hopeful that we could try to make sense of more general gaugings of these theories to extend the classes of n equals to 1 superconformal theories we know in general. And furthermore, there's been recent work on n equals to 1 superconformal field theories that are kind of Argyres-Douglas-like, but not exactly. I guess you can ask me later if you want to know more about that. But I'm kind of hopeful that we can relate these sort of n equals to 1 deformed Argyres-Douglas theories to this larger class of n equals to 1 theories that have been discussed recently in the literature, which I think might have something to do with this sort of picture. And so, yeah, I think there are some interesting questions to look at there. But I'll stop here. So thank you very much for your attention.
Yeah.
May I ask? I'd like to understand the simplest example, P equal 2. If at P equal 2, the Argyres-Douglas theory is infrared dual to adjoint chiral.
Exactly, free adjoint chiral.
Free adjoint chiral. And yeah, if we gauge SU and then it becomes SQCD.
Right. So then if we gauge SUN, then we get the trace X cubed. It becomes SQCD, and this is supposed to be dual to the trace X cubed type fixed point.
Yeah. So if we admit the infrared duality of Argyres-Douglas and free chiral multiplet, then your conjecture is true at least for P equal to.
Yes,
right?
that's right.
But on the conformal window at P equal to, these theories have different window, right?
Let's see. So
I'm confused at that point.
let's see. So also for P equals 2, there's a range from n over 2 to NF equals n over 2 to NF equals 2n, where the window where there's a proposed conformal window. That's the statement.
So are you saying so on the overlap of two conformal windows, they match or?
That's right. Maybe it's confusing that I'm using the word conformal window. So I'm what I'm showing on this slide is first independently of the SQCD theory, like, what is the range of parameters for which we are arguing that this deformed Argyres-Douglas theory flows to a fixed point? Like, forget about the duality, just like, when does it flow to a fixed point? There are various consistency checks, and those consistency checks give these bounds. Separately, again, totally independent of any statement of duality, like, what's the same window for just adjoint, like the adjoint SQCD theory with this superpotential? And the statement is that it's within this bound. So therefore, I'm like the proposed conformal window for this duality is where these overlap. And so like that's why I was like emphasizing these bounds, because like this statement of like a duality conjecture would be meaningless if there wasn't a region where you know, I'm arguing that these fixed points exist and are the same. You know, I'm saying it's the same fixed point, so you know it should exist within the same window, or else it's just a contentless statement. And so that's what I meant by this slide.
Sorry, I have a question about this slide. So I'm not familiar with this kind of topics. So, but my question is, how can I estimate the beta function in the non-Lagrangian theory? So
Good.
yeah.
Good. So we can't. So basically, what you can do is you can estimate or you can compute like what the contribution to the overall beta function is from this like non-Lagrangian block. So like that's something you can check. Like you can check. I forget which paper did this. Maybe Del Zotto and Chikati. I could give you the reference. But like what I could check is like what the contribution is of this block to the beta function, and then if I have other like you know more weakly coupled contributions that are easy to understand, I can basically add them up. And so this is something that you can do like even just in the normal class S program. Like I can understand like what some of these like strongly coupled blocks like contribute to the like one loop beta function. And that's how I get this like upper bound. Yeah. Thanks.
Thank you very much.
Yeah.